In the last video, we left off talking about mean value theorem, which we can abbreviate as MVT from here on out. And what mean value theorem told us is that if f of x is continuous and differentiable on some interval from a to b, then there must exist some value of c on that interval from a to b such that the derivative of the function f at that point c is equal to the average rate of change of the function over the entire interval. And the real world analog of that theory could be the example of, let's say you're running a race, and over the course of the entire race, your average speed is 5 miles per hour. What the mean value theorem tells us is that if your average speed over the entire race was 5 miles per hour, certainly at some point during the race, you must have been running at an exact speed of 5 miles per hour. And in this video, what I want to focus on is why this theorem is actually important, and some applications of this theorem, because it's not immediately obvious, but this simple theorem is actually one of the foundational theorems of calculus, and if it did not exist, then we wouldn't have calculus as a field. And it might not be immediately obvious why that is the case, but looking at a couple trivial examples of applying this theorem will show you why this is so important. So in order to get a sense of that, let's just consider the case, for example, where f prime of c is greater than 0. What do we know about f if we know that f prime of c is greater than 0? Well, the key here is to realize that in this definition for their mean value theorem, b is representing the upper bound of some interval. You could think, for example, if you're dealing with the interval from 0 to 4 or the interval from 4 to 0, that's the exact same interval. And so the conventions of the mean value theorem are just to set your upper bound of the interval equal to b and that lower bound equal to a. And when you're doing that, that means that b is always going to be greater than a, and that implies that b minus a will always be greater than 0. And so if we know that f prime of c is greater than 0, and we know that that's equal to f of b minus f of a over b minus a, and we know that b minus a is greater than 0, that implies that this expression in the numerator here, f of b minus f of a, must also be greater than 0, because the only other possibilities would be that f of a was greater than f of b, which would make this some negative value, and then f prime of c could not be greater than 0. It wouldn't be possible. It would be some negative value. And of course, the same would be true if f of a was equal to f of b. Then this whole thing would reduce to 0, and f prime of c could not be greater than 0, which is our assumption here, that f prime of c is greater than 0. And so if we know that f prime of c is greater than 0, what that tells us is that f of b minus f of a, our numerator here, must also be greater than 0, which implies that f of b is greater than f of a. And if we know that this is the case, what that tells us is that this is sufficient to prove that if f prime of c is greater than 0, then f is increasing. F is increasing at the point c. And similarly, if we knew that f of x was, or the first derivative of the function f of x was positive for any value of c in the interval from a to b, for example, then we would know that the function is increasing over that entire interval. This is something that we've definitely alluded to before in calculus, because it just seems so obvious that if the derivative represents the rate of change, and that is a positive value, then the function must be increasing at that point. And while it is obvious, it is intuitive, and this wasn't even proved around the time of Newton and Leibniz because they just accepted it as clearly true. We didn't get the tools to be able to prove that until we had this mean value theorem. And part of that comes from the condition here that the function must be continuous and differentiable. But if you know all of this stuff, you could prove this. We did that in the last video. We proved the mean value theorem. And by proving the mean value theorem, you have the tools to prove that if the function's first derivative is positive, then it must be increasing. And so that's the first application of the mean value theorem. That's pretty trivial. Very similarly, in fact almost identically, we know that if f prime of c was less than 0, then that would tell us that f prime of c be equal to f of b minus f of a over b minus a. Once again, this doesn't change. This must be greater than 0, and this must be less than 0. And so that tells us that the numerator here must be less than 0. If f of b is minus f of a is less than 0, that tells us that f of b must be less than f of a, meaning the function must be decreasing if f prime of c is less than 0. So similarly, we could prove that with mean value theorem as well. And the last of these trivial examples is going to be the case when f prime of c is equal to 0. The only way that this can happen is if this numerator here is equal to 0. And the only way that f of b minus f of a can be equal to 0 is if f of b is equal to f of a. And with this information in mind, what would be a function where this would be true for any value of x on the interval? So let's consider some function of f of x such that f prime of x is equal to 0 for any value of x out of all of the real numbers. What would be a function that would satisfy these conditions? Well, if we have to pick a function where f of b is equal to f of a for any interval of values, the only possible function that could satisfy that condition would be the function, or would be some form of f of x is equal to a constant value. That is the only way that this could be true for any value of x that you would input into the function. And so by mean value theorem, we're also able to prove that not just that the derivative of a constant is equal to 0, but that the only possible function which could satisfy these conditions, that the derivative is equal to 0, would be some constant. That's the only possible function that could satisfy those conditions. Once again, this is something that seems very obvious, but we didn't have the tools to prove it until we have mean value theorem for this reason right here. In order to talk about a not so trivial application of mean value theorem that is definitely applicable to single variable calculus, we're going to have to introduce this concept of the generalized mean value theorem. In order to do that, I want to remind us of what the mean value theorem tells us with a analog to the real world, a real world example of what mean value theorem might say. So MVT would tell us that if your average speed over the course of an entire race was 5 miles per hour, then at some point during that race, you must have been running at 5 miles per hour. And it makes pretty good intuitive sense. We proved it in the last video. But right now, we're going to introduce this generalized mean value theorem, also called Cauchy's generalized mean value theorem. And that's going to tell us something similar, but a little bit different. It's going to tell us if mean value theorem told us this, then Cauchy's generalized mean value theorem would tell us that, which I've abbreviated GMVT, that if my average speed over the course of a race was twice as fast as yours, at some point during the race I must have been running twice as fast as you at that instant. So I've erased that reference to mean value theorem, and I've just left this reference to what a real-world analog of generalized mean value theorem would look like, and I want to see if we could translate this from the real world into mathematical terms. And so if we're looking at the ratios between the instantaneous rates of change of two different functions versus their average rate of change over some interval, and we're saying that at some point in that interval, it must be true that the ratio between the instantaneous rates of change of the two functions is equal to the ratio of the average rates of change of those two functions over the entire interval, we could write that pretty succinctly using derivatives. So for example, if I had two different functions, f of x and g of x, I could write that that f prime of some value c on the interval from a to b, so I'll say c is on the interval from a to b, then the ratio of the derivatives of these two functions at the point c must be equal to the ratio of the average rates of change of these two functions over the entire interval from a to b, which we know how to calculate that. That's just the same as with mean value theorem. And so for g of x, that would be g of b minus g of a over b minus a. And this is literally just taking this idea here and representing it in mathematical terms. This would be me running twice as fast as you at some point c, And this is the idea that I ran twice as fast as you over the entire interval. This is my average rate of change over the interval, and this is your average rate of change over the interval. This is my instantaneous velocity at some point. This is your instantaneous velocity at some point. And so representing this in mathematical terms, what we'll notice is that these denominators will cancel. And we'll be left with this is equal to f of b minus f of a over g of b minus g of a. And let's see if we can prove that this point C would exist on the interval from a to b. The way that I'm going to go about this is I'm going to multiply both sides by g prime of c, and I'm going to subtract f prime of c just to sort of isolate everything onto one side. And what I'm going to get is that 0, which is all I'm going to be left with here after I carry out that multiplication and subtraction, is going to be equal to f of b minus f of a over g of b minus g of a. And this is going to be multiplied by g prime of c, and we're subtracting f prime of c. And what I'm noticing here is that this is true only for one point, and that point would be equal to c, or perhaps there are multiple points, but this is just true for a point. This is what we're talking about. We're talking about the point c where this fact holds up. But we could just as easily consider this as a function. I'm going to call it h prime of x. And I'm going to say that this is equal to the same thing, but for generalized terms. So it would have the same expression here. This is just going to be a constant. Oh, whoops. Pushed the wrong keys. This whole thing here is just going to be some constant because it represents the function evaluated at some point minus the function evaluated at some other point over a different function evaluated at some point minus that same function evaluated at some other point. And so all of those are just going to be numbers. So there's no variables in this expression. It's just one giant messy coefficient. And so I'm going to define a new function whose derivative is equal to the general form of this function. And then what I'm going to do is I'm going to try to consider what function out there would represent h of x, wherein when I took the derivative of it, it would give me this expression here. And at first this does seem daunting, but it's actually not that hard because, like we established, this is a constant, and a constant multiplied by a function, when you take the derivative, is just going to be that constant multiplied by the derivative of that function. And so, in other words, the function whose derivative would be equal to this would just be equal to f of b minus f of a over g of b minus g of a, just that constant out front, and we would have g of x here minus f of x. When we took the derivative here, we'd be left with this constant multiplied by g prime of x, and because we're not multiplying these functions of x together or anything like that, it's just a difference. The derivative here would just be, we'd subtract the derivative of f of x, and we get this. And now what I want to consider is what do we get when we evaluate this function at the point a, at the beginning of our interval? Well, what we would have to do is find a common denominator, and so we would have to multiply this f of x here by something in order to get a common denominator here with this expression. And the way I would do that is I would multiply the numerator and the denominator by g of b minus g of a to get a common denominator, and it wouldn't change the value of the function because we would essentially just be multiplying by 1. And so what we would get here is we would get f of b minus f of a. All of this is going to be divided by some big expression. This is going to be multiplied by g of x, but in this case we're plugging in a for x, and so it's going to be g of a. And then we would subtract, in order to get a common denominator here, we had to multiply f of x by g of b minus g of a over g of b minus g of a. So we have g of b minus g of a here. It's going to be in parentheses, multiplied by f of a, plugging in a here. And we're dividing this whole expression by g of b minus g of a. And when you carry out this process, what you'll notice is that here I have minus f of a g of a. And then here I also have minus f of a g of a. However, there's a negative, so this is going to turn into a positive, and these two are going to cancel. And so really, what I'm left with is just the first two terms of this expression. And so this is going to cancel, and this is going to cancel, and I'll be left with f of b times g of a minus g of b times f of a. All of this is going to be over g of b minus g of a. And what happens to the function when we evaluate it at the point b? Well, if you carry out the same exact process, but you place b in for x instead of a, you'll get f of b minus f of a times g of b here, and we would get g of b minus g of a times f of b here, and we would divide this entire function by g of b minus g of a. That's just inputting b in for our x values in this expression. And when you evaluate this, what you will notice here is that if you look here, you'll get f of b times g of b, and then here you'll get f of b times g of b, and you're subtracting those, so those are going to cancel, and what you're left with is negative f of a times g of b, and you are left with negative g of a times f of b, but there's a negative here, so that's going to turn into a positive, and you'll be left with f of a times g of a, or times f of b times g of a, because this would become a positive, and you would subtract f of a times g of b, and all of that is going to be over g of b minus g of a. And now let's consider this. We know that f of x and g of x are both continuous functions. This is just one of our presuppositions for this generalized mean value theorem. So these are both continuous differentiable functions, and we know that the function h of x is composed of a constant multiplied by a continuous differentiable function minus a continuous differentiable function. So this function h of x is also going to be a continuous and differentiable function over the interval from a to b. We also know that the function h of x evaluated at the beginning of the interval h of a is going to be equal to the function evaluated at the end of the interval at h of b. And so what that tells us is that we can actually use Rolle's theorem here. Rolle's theorem applies, which is just a specific application of the original mean value theorem. And that tells us that there must exist some c on the interval from a to b such that h prime of c is equal to 0. And we know from how we originally designed this entire function, or how we originally started working this problem, that when h prime of x is equal to 0, that we're going to get what we started with. When h prime of x is equal to 0, we're going to get this, and working backwards, we will get what we originally came up with, which is that the ratio of the instantaneous velocities of that function at some point c must be equal to the ratio of the average rates of change of those two functions over the course of the entire interval. We know that this fact is going to be true for some point c if the derivative of this h of x function that we devised is equal to 0. And we just proved that there is a point on the interval from a to b, there's a point c that exists in between those two endpoints from a to b, such that h prime of x will equal to 0, and this fact will be true. So therefore, by Rolle's theorem, we know that there must exist some c on the interval ab such that h prime of c is equal to 0. Therefore, we know that f prime of c over g prime of c is equal to f b minus f of a over g of b minus g of a for some c on the interval from a to b. Now that probably felt like a pretty long tangent, and if it felt like a lot, don't worry, because the generalized mean value theorem is not going to come up very frequently, especially not in Calculus 1. It's very useful in real analysis and other different fields of mathematics, but at the current point, in calculus, it doesn't come up that frequently. But it was necessary because we needed to prove L'Hopital's rule, which is something that does come up pretty frequently in Calculus 1 and beyond. Now, in order to introduce L'Hopital's rule, I want to remind us of the video that we did on the squeeze theorem, wherein we use the squeeze theorem and a geometric argument in order to prove that the limit as x approaches 0 of this expression here, sine of x over x, was equal to 1. Now I want you to consider what happens to this function if we try to solve this limit by direct substitution, just plugging in 0 for x here. Well, what we're going to get is we're going to get sine of 0 over 0, and that's just equal to 0 over 0. And so this is pretty complicated. I know that we used a geometric argument and we actually found a way around this situation, but at its face, by direct substitution, this is not very promising. It doesn't tell us that the limit doesn't exist per se. It's not giving us some value that's impossible. It's not 1 over 0, for example, but it is indeterminate. There's no definitive answer here. But we did find, via a geometric argument and the squeeze theorem, we were able to prove that this limit does indeed exist and that it is equal to 1. And so L'Hopital's rule is going to be an alternative to that allows us to deal with these situations much more generally whenever we wind up with a indeterminate limit, something that looks like this, 0 over 0 or infinity over infinity, something of that nature. Whenever we're confronted with that, we can use L'Hopital's rule. So I want us to consider the situation a little bit more generally. So let's say that we have a pair of functions where the limit as x approaches some value a of those two functions, f of x over g of x, is equal to f of a over g of a, which winds up giving us an indeterminate form, 0 over 0. And now what I want to do is consider the range of x values from a to x. And I want to consider what happens when we apply the generalized mean value theorem over this interval of x values. Well, what that tells us is that there must exist some value c where f of x minus f of a over g of x minus g of a is equal to f prime of some value c, f prime of some value c over g prime of that same value c. And at its face, this is not very noteworthy. It doesn't seem to matter that this is the case. But what we need to realize here is that we're considering the range of x values from a to x, and c is going to be some value in between a and x by that generalized mean value theorem. And so I want you to consider a number line, for example. And let's say that our a value is right here, and our x value is right here. Our c value is going to be somewhere in the middle. Let's just say it's there. One thing to realize here, and I made a mistake here, this should be g of a, not g of x, but we'd have f of x minus f of a over g of x minus g of a. We know that f of a and g of a are both equal to 0. And so this is going to be equal to f of x over g of x, which is equal to f prime of some point c on the interval between a and x over g prime of that same point c. And now what I want us to consider is what's going to happen when we take the limit as x approaches a, as we tried to do up here. Well, when we take the limit of both of these expressions, the limit as x approaches a, what's going to happen here? We're going to get f of x over g of x, and then we'll take the limit on this side. We'll get the limit as x approaches a of f prime of c over g prime of c. Now consider that c is always going to be in between these values x and a. And so what happens if we take the limit as x approaches a? It's going to push this in. And c must always necessarily be in between these two values. So if we take the limit as x approaches a, that's the same as saying that c will approach a as well. So taking the limit as x approaches a, given that c must be in between a and x, means that we are essentially taking the limit as c approaches a. And so if this is equal to the limit as c approaches a of f prime of c over g prime of c, this is essentially the same thing as the limit as x approaches a of f prime of x over g prime of x. It's just using c as a different variable. And so with all of this information, we have shown that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. And this is L'Hopital's rule. And don't be thrown off by this switch of variables here from c to x. C is just a dummy variable here because it is some different value that has to exist between a and x, and I just chose c because that's what we were using when talking about the generalized mean value theorem. But switching it from the limit as x approaches a, switching it from the limit as c approaches a of f prime of c over g prime of c to x instead of c does not change the mathematics at all. And so what we've demonstrated is that if we're trying to take the limit as x approaches a of f of x over g of x, and we get some indeterminate form, like 0 over 0, we could take the limit of the derivatives as they approach x over a, and it will give us the same answer. These two expressions are equivalent by L'Hopital's rule, which we just proved. And so let's test that over here on the limit that we were dealing with in a squeeze theorem video, wherein we use the geometric argument to prove it's equal to 1. Let's try using L'Hopital's rule on the same expression. And so with that, we would say that the limit as x approaches 0 of sine of x over x, that's going to be equal to the limit as x approaches 0 of the derivative of sine of x over the derivative of x. Well, the derivative of x is just 1, and the derivative of sine of x is cosine of x. And now we can use direct substitution here because we could just plug in 0 cosine of x, and we'll get 1 over 1, which is just equal to 1. And so we do see agreement here between L'Hopital's rule and the geometric argument that we used from the previous video. But the thing to realize here is this is so much easier. This was just basically one step. We just had to differentiate, and then we were able to plug in the values. This is so much easier than having to draw out the unit circle and find different segments of areas and then find some relationship between them and see how they change with respect to small changes in theta, and then using the squeeze theorem to prove that it's equal to 1. This is so much faster, and it wouldn't be possible without the mean value theorem. As a final note here, I just want to point out and reiterate that this is only applicable when we have these indeterminate limits. And so it's only useful, L'Hopital's rule, when we have the limit as x approaches a of f of x over g of x being equal to either some 0 over 0 form or these positive or negative infinities, these indeterminate forms. This is the only situation where this is applicable. You can actually see exactly why that's the case when we do this step and we apply the generalized mean value theorem. You can see the only way we were able to advance into the next step is because this didn't present any problems. If this was not equal to 0 over 0, there would be a confounding variable here that would prevent us from moving forward with the proof. And so I just want to reiterate that this is only applicable, only apply L'Hopital's rule when you have these indeterminate forms of the limits. I hope that was illuminating, and I hope it gave a chance to see how mean value theorem can be pretty useful. I know I didn't prove this case when we're dealing with these infinite indeterminate limits, but it's a lot longer, and I can sense this video is already getting pretty long. So I'm going to see you guys in the next one. Thanks to all for watching.